Greetings and welcome back. So, where we are in the course is we're now going to undertake a really, to my mind, very fun part of how we think about evolution, and that's the branch of the subject that's known as population genetics. And I'm going to give you what amounts to what I would call a superficial treatment of that, in the sense that one can have a whole course on it. There are whole books about it. They're very mathematical and in a fun way that I think that many of you would enjoy. I'm going to try to keep it relatively simple, but not shy away from doing mathematics. So, what's going on in this part of the theory of evolution? The idea is basically just as we're used to in other domains of science, we make some abstractions. There's this triumvirate of abstraction, idealization, and simplification. And we're doing all of those things at once, in the sense that we're going to think of a diploid organism, such as you and me, as being a bag of a bunch of independent genes. Each gene can come in only one of two flavors. So, in other words, it's going to be what amounts to a single locus, two allele model. So, in other words, what I mean by that is that each of us, for the gene of interest, either harbors the genotype AA with the capital A's, or capital A lowercase a, or lowercase a. Those are the three possible genotypes. And of course, especially in light of modern computers, one can do better than that. We could generalize, but the conceptual ideas won't have changed. So the the idea of the next couple of vignettes is that I'm going to tackle four of the five rows that you see in this diagram, and let me just remind you then of what the abstraction is. So the abstraction is that, as I've already said, that each gene is its own thing. In other words, each gene within me, within you, within the lizard, within the snake, whatever, doesn't know anything about the other genes. We know that that's not true. We know that there are things like crossing over. We know that there are chromosomes, and things go along for the ride together on chromosomes. So that part of the abstraction we know to be not true, but that doesn't make it not useful. So we're going to go down this path of, I have a bunch of Scrabble letter bags, and each one of them is one gene, and there's only two letters, capital A and lowercase a, and they come in a certain quantity. And then what I'm going to do is I'm going to figure out how to get the next generation on that gene, and then the organism is the whole collection of all of these genes, which for the moment we're treating as being independent. And so what we're going to do is we're going to try to write a mathematics of the frequency of the different alleles. So in our case, unlike this diagram, in the diagram what you see is that there are, maybe 6 or 7 species or alleles, and the evolution corresponds to changing the frequency of those different alleles in the population. So that part we're going to stick with, but we're going to do it in a way that's really simpler than what you see here, because we're only going to do the two allele case. Okay, and so in turn, the plan is, first we're going to do what you might think of as the analog of Newton's first law of motion. Let's remember our mechanics. The first law of motion says that a body will continue in its state of rest or of uniform velocity unless acted on by a force. So this is already hugely provocative. The idea that was addressed by Hardy and Weinberg was, if I have uneven distribution of capital A and lowercase a, let's say we have way, way, way more capital A's than we have lowercase a's, you might have thought that in the population that the little a's would be gobbled up, and over the long haul it would be all strictly capital A. And what we'll see is that the neutral model says, nope, it'll stay, sorry, not the neutral model, the null hypothesis of Hardy-Weinberg equilibrium is it will stay with those frequencies unchanged in the absence of driving forces. So what are the kinds of driving forces? Well, the one that almost all of us know about and probably think of the most is natural selection. The idea that there's some force that tends to favor little a over big A, like that could happen. And we'll talk about such things. We could also have mutation, and that is that big A gets turned into little a, or little a gets turned into big A, and that little cycle of kinetics can alter the frequencies of genes. But then there's also genetic drift, which we'll talk about in the next vignette. We'll talk about in some detail. So at any rate, that's the scope of the investigation. We want to do this abstraction, idealization, and simplification. So here's my representation. So I think of a given gene as corresponding to an urn, and the urn contains a bunch of alleles. And what we're going to do is, the first thing we need to do is we need to work out what I'm going to refer to as a kinematics. So you'll remember from mechanics that kinematics refers to the geometry of motion. It's basically the accounting. It's the part in which we keep track of the positions and the speeds or velocities of the various particles. That's the kinematics. So here the goal is, I'm going to put this in quotes, the kinematics of population frequencies of the population. So I'm going to introduce some variables. NAA is the number of individuals of genotype big A, big A. And then NA little a is the number of individuals of genotype big A, little a. And then finally, N little a is the number of individuals of genotype little a, little a. And finally, the total, N tot is the total number of individuals. And then I'm going to refer to P sub A as the probability, not number, but it's the probability of an A allele, a big A allele, and P little a is the probability of a little a allele. So that's a bunch of notation, but it's also really a statement about the nature of the population. We can notice a few things. So we can notice that, let's see, the frequency of big A is given by, NAA over N tot, and similarly FA little a is NAA over N tot, and then finally F little a is N little a over N tot. So those are the frequencies. In other words, I'm basically normalizing in order to figure out the relative probabilities of the different genotypes. I can also make the observation that PA is going to be given by 2 times NAA plus NA little a divided by 2 N tot. Why is that? The numerator says, well, for every N big A, I pick up 2 big A alleles, and for every N big A little a, I pick up 1 big A allele, and then if I'm trying to find the probability of big A, I need to divide by the total number of alleles, which is 2 times N tot, because these are diploid organisms. And P little a is, by analogy, 2N little a plus N big A little a divided by 2N tot. So those are our kinematic variables. Those are the things that we want to reason about. So now let's talk about what Hardy and Weinberg were curious about. So they said, well, I have a parental generation, which I show you here. And you can see that this parental generation is made up of, they use slightly different notation than I did, but it's made up of a bunch of diploid individuals. There's 3 types of diploid individuals. I can either be an A1 A1, an A2 A2, or an A1 A2. That's it. There's only probabilities. And the thing that they wondered about is over time, in the absence of any sort of sculpting of the population by selection, by mutation, and as long as we're thinking about an infinite population, which is to say that I don't achieve the fluctuations that I'd expect in a small population. They wanted to ask: is the genotype of the population stable? Is the fraction of AAs, A1 A1s, A1 A2s, and A2s is A2 A2s is that constant? So here's the concept. The concept is that they imagine the parental generation as this Scrabble bag, which is shown in the middle, which is called the gamete pool. So I basically have inside of that bag, I have 2 times number of individuals, 2 times what I call then total tiles. Each tile is either an A1 or an A2. And then the way the game goes is to get the offspring generation, I reach into the bag and I pull out a letter and I look at it. And then I say, okay, well, that's the first allele on individual number 1 in the next generation. I put that tile back in, and then I shake and I reach in and I grab another one and I look at it. And what I find is that whatever I got, I assign in the offspring generation those 2 tiles to individual number 1, and then I do this n-tote times. In other words, I select n-tote individuals by reaching into the gamete pool and pulling out the tiles and assigning them. Okay, so the question again, I want to, in a way, I want to ask you, or to get you to imagine the profundity of the thing that Hardy and Weinberg were thinking about. They just had this idea that maybe if there were a lot more A1s than A2s, that over time the A2s would just drop out of the population altogether. And they wanted to know, is that the way the math plays out? So let's figure out what is PA prime, or maybe I'll call it PA at n+1. So this is the probability of an A allele in the n+1th generation. Well, how do I get that? What I do is I take 2 times the frequency of big A plus f of big A little a. Why is that? Because what I'm doing is I'm going over to this right hand bag, and I'm asking how many AAs are there, or in their language, how many A1 A1s are there? However many whatever frequency that I count, I multiply that by 2 because each one of those AAs carries 2 of the capital A allele. And then in addition to that, I add on the frequency of FAA, A little a, and that gives me, what do I want to say? I think that I screwed this up. So let me try this using the numbers. So I have 2 times NAA. I'm almost sure I screwed that up, so I beg your forgiveness. 2 NAA plus NA little a, and then this is divided by 2 N tote. That's the same as NAA over N tote plus 1/2 times N big A little a over N tote. So that's what I get. And this is given by, well, I should say this is called FAA, and this one is 1/2 FA little a. So far, so good. Okay, sorry about my screw up. Now, what is FA big A big A? That's given by PA at generation N squared. And then I have plus 1/2. And then what is f big A little a? That's 2 times p a at n q. What do I want to say here? P a at n 1 minus p a at n. Why is that? Because the probability of getting a big A little a is PA times 1 minus PA, that's the P and the Q, and then I need a factor of 2 because that's this factor of 2. I need this factor of 2 because I could have picked big A first and then little a, or little a first and then big A. That's the way that this could have gone down. So I could have gotten either of those eventualities. So we can keep going with this. So this gives me PA at n quantity squared plus PA at generation n times 1 minus PA at generation n, which is equal to PA at generation n squared plus PA at generation n minus PA at generation n squared, which is equal to PA at generation n. All right, this argument, I don't know. I mean, maybe some people think, I know they teach it in high school, but I think it's very subtle. I think it's philosophically subtle. You know, what they're asking is what happens to the allele frequencies in an evolving population in the absence of any sort of rule which favors one allele over the other or alters the allele frequencies upon mating. And so that's the first thing. And then the point I'm making is that I'm imagining a large population so that, you know, the average, basically I'm thinking about what's going on with the averages. So the question I asked and examined mathematically was, I said, what is the probability of getting a big A in the pool in generation n plus 1? How do I think about that? I go from generation n to generation n plus 1. Generation n plus 1, there's still n-toed individuals. And I just I take all of the alleles and I put them in one giant bag, which I'm calling the gamete pool. I want to know about the probability of an A one generation later. How do I do that? Well, I look at the individuals. What kind of individuals are there? There's some big A's, there's some big A little a's, and there's some little a's. And if I want to find out the frequency in this next generation, I take 2 times the number of big A's in that new generation, plus the number of big A little a's in that generation, and divide by the total 2 times the total number of individuals, and that ends up showing me that, you know, the frequency in the new generation of big A is f big A plus 1/2 f big A little a, and then I basically I know what those probabilities are because I know how I drew from the gamete pool. I know what f big A is, so it's given by this expression, and I know what f little a big A is. That's this thing. Then I do the algebra, and when all the dust settles, what I'm left with is PA at n plus 1 is equal to PA at generation n. And so this is the analog of Newton's first law for population genetics. Which is to say, if you have a large enough population, you know, in the limit that n-toed is infinitely large, then what will happen is whatever frequency distribution you have of big A and little a, it will not change in the absence of the kinds of driving forces that we referred to up here. So that's the end of this vignette, which is basically an introduction to the Hardy-Weinberg equilibrium. It doesn't really matter that much if you do the calculation. I mean, it would be good, but the thing that I want you to carry away is that this is a large population size limit result, and it's very deep. because it tells us that our expectation should actually be that the population is not evolving over time. We need some sort of driving force to achieve that.